In this video, we're going to talk about a heat engine. We'll start by talking about generic heat engines and defining exactly what they are. So a heat engine, we'll start with this definition here. It's a device which operates in a thermodynamic cycle. We'll stop there, highlight that. That's one of the key points. So it's operating in a cycle. And it does positive work through the transfer of heat from a high temperature body to a low temperature body. So work out, heat in. And it operates in this thing that we call a thermodynamic cycle. We'll define exactly what that is kind of by showing examples of what that is, and hopefully that makes it clear. We'll first draw just a black box heat engine. So if the box that I have here, that's our control volume. We're not going to worry exactly what's happening inside. I have this little circular arrow drawn here to denote the fact that this is actually operating in a cycle. Right? So you can think of there's a single fluid going around in a circle inside of here, going through some sort of different processes. We don't know what that is. That's a black box. But what we do know is we have a high temp up here and a low temp down here. We'll call that TH and TL. And what's happening in our heat engine is we have heat flowing into our black box from the high temp and flowing out of our black box into the low temp, QH and QL. And out of our black box, we're getting some amount of work. Right, so this is the schematic drawing of that definition that we just had, where we're allowing heat to go from high temp. Something's happening inside of our black box. It ends up, we pass some of that heat to the low temperature body, and the rest is converted into work, W. If we want to talk about the efficiency of a heat engine, this is a standard definition of efficiency for these kinds of systems. We would talk about the thermal efficiency. How efficiently are we using the heat? Really, how efficiently are we converting that heat into work? We can measure that by just the work out over the heat in. Another way to think about that is what we want, right? In the heat engine, we're trying to produce work. So that's the work output, the net work output is what we want. And sorry, I can't write, what we pay for. So that's going to be kind of the key metric for a heat engine is what do we want? Well, we want work out. What do we pay for? We pay for the heat that we have to put in, which in this black box, that would be QH. We don't pay for QL. That's energy that we lost. That's the energy that we didn't get to use. So when we're looking at thermal efficiency, we're talking about the work output over the total heat input. Just a key note is this is not isentropic efficiency. That would be like a single device. Sometimes we'll call isentropic efficiency device efficiency, or you may hear that. This is a cycle efficiency, the efficiency of, as we'll see, multiple different devices or multiple different steps or processes happening consecutively. So it's the efficiency of kind of the whole business rather than the efficiency of a single component. We can look at the thermal efficiency generally. If we look at the picture we want to put variables to it, if we look at this black box picture, we can see that the thermal efficiency would be W over QH, right? That should be fairly apparent. The net work that we're getting out, that's W. The heat that we're putting in, that's QH. But because of conservation of energy, we can do an energy balance and say that, well, the work that we're getting out is just the heat that we put in, QH, minus the heat that we lost, QL, because all of those things have to match up. We'll say because of the first law, QH equals QL plus W. So sometimes you'll see this written, and we'll use it here in a second, QH minus QL over QH. Another way to write this, right, we could split this fraction, and this is 1 minus QL over QH. So these are just a couple different ways of writing the same thing. But really what we're looking at is this one here, and we're just using the first law to rearrange it a little bit. I'll just make a comment. This is the net work output. So it's the total amount of work that we're getting out of the system, factoring in all of the work that we're getting out, and then we would be subtracting all of the work that we would have to put in if there's any. So we're going to look at a little bit more at one special case, which we covered briefly in class, which is called the Carnot cycle. So here's the figure that we had in class for the Carnot cycle where, okay, so this in our example before, that would be our black box. Before, and now we just have actually put some different things inside of our black box. You can see it's operating in a cycle where we would have something go from 1 to 2 to 3 to 4, back to 1 to 2 to 3 to 4, back to 1, and we could kind of have it keep going around forever. We're letting heat pass from our high temperature reservoir or hot reservoir to our cold reservoir. In this case, we have some work going in, which I've called minus WC, and we have work going out. We could combine those and talk about a net work output. As we said in class, the Carnot cycle is 4 ideal processes. 2 of them are isothermal. So as we go from here 2 to 3, right up at the top, that's an isothermal process. As we go from 4 to 1, that's also an isothermal process. And this process 1 to 2 is adiabatic, and 3 to 4 is also adiabatic. So we have 2 isothermal, right, where the temperature is constant, 2 adiabatic, where Q is 0, and all 4 of these processes, because they're ideal, they're all reversible. So this is, right, all reversible. And what we find in the Carnot cycle, right, you can kind of split it up because of the 4 different processes. You can kind of split it up by halves. So this is the whole bottom of the system is all at TL because that process 4 to 1 is isothermal, and the top half of the system is all at TH. And that's what you can kind of think of. So we have the top of our system is all at a constant temperature. The bottom of the system is all at a constant temperature, and we have these kind of 4 steps around the cycle. One way, and we touched on this briefly in class, is we can think about this in a temperature entropy diagram. because we have 4 ideal processes, we can look at how those look on a temperature entropy diagram, where we have, again, 2 adiabatic reversible processes. Those are the vertical lines, and we have 2 isothermal reversible processes. Those are the horizontal lines. In class, we said that then this area here, right, all the way down to 0 Kelvin, this is QL equals TL delta S, and the, we'll use red, this area, again, all the way down to 0 Kelvin, is QH equals TH delta S. And we can use these 2 equations, right, because we have reversible isothermal processes. So these are special cases of our generic equation for a reversible process, which is Q equals the integral of T ds. So this is for a general reversible process. Right, so this simplifies to just T delta S on the right-hand side when we have an isothermal process. We have 2 isothermal processes, that's why we get these equations. For a Carnot cycle, the thermal efficiency, we can look at it in a couple different ways. Again, it is still the net work output divided by the heat input. So in this case, if we scan up, the total work out is going to be, well, I guess WT plus WC. So this is WT plus WC, right? Noting that is should be a negative value. Because that's a work input. So that's what I tried to kind of highlight here with saying that it's negative WC. That's work that's going into our system. So that's going to be a positive number for WT and then plus a negative number for WC, all over QH. Or we can write that the kind of using the simplification that we did before, that this is QH minus QL over QH, which would be equal to 1 minus QL over QH. Which in this case would be equal to 1 minus TL delta S over TH delta S. The T delta S would cancel out. So we have a special equation for the Carnot efficiency, which is 1 minus TL over TH. So there are just a couple things to note on this equation. Temperature has to be in Kelvin. Not degrees Celsius. And it has to be in Kelvin because entropy is a thing in Kelvin. You can, if you just look at the Carnot efficiency, right, we can't have that becoming a number greater than 1 because that would mean that we're creating energy out of nothing. And that would happen if we had, say, a TL of less than 0 degrees Celsius if we were using Celsius. So you can kind of directly see from that that our numbers have to be in Kelvin. But that's an important thing to remember. The thing that I typically like to note is, right, if you're doing temperatures and you're doing anything with entropy, it always has to be Kelvin. And just kind of generally in this class, usually you're almost never wrong if you use absolute temperature. You are often wrong if you use Celsius, or Fahrenheit for that matter. Okay, so that's one kind of key thing to note. The other thing is that this is interesting because it tells you that the efficiency, or the maximum efficiency that you could do for any heat engine, that's what the Carnot is. It's a maximum. So Carnot is the best heat engine, and that the maximum, it really only has to do with the two temperatures involved. What's your hot temperature and what's your cold temperature? Just kind of as a concrete example, you can think of, okay, what's the hot temperature for example, a car engine? Well, the hot temperature is the temperature that the combustion reaction is reaching in your engine. What's the cold temperature? That's the temperature of the ambient environment where your exhaust is going out the back of your car. So we're always going to be limited by those two temperatures. What's our hot temperature and what's our cold temperature? And we're going to get a more efficient process, a more efficient heat engine as our TL decreases. So efficiency goes up as TL goes down, or as TH goes up, or some combination of the two. So we're going to use heat engines. We're going to keep exploring some of the more of the details of real heat engines. You're going to have an example in the participation assignment for this week where you'll go through step by step, analyzing kind of in nitty-gritty detail a Carnot heat engine, and then come back and be able to evaluate this equation, be able to look at some of the different steps and pick that apart. And then in the homework, you're going to go through a different heat engine process, which is called the Rankine cycle. It's still a heat engine where we're putting heat in, getting work out. It's just going to be a different process than Carnot. And as we continue on in this class, we're going to explore other cycles sort of like this, which are also heat engine cycles, and then kind of comparing all of those back to this cycle, the Carnot cycle, because that's the ideal heat engine. So look for more heat engine stuff coming up soon this week, but then also expect this to be kind of a theme of the course over the next number of weeks.